Welcome to our lecture video for statistical hypothesis testing. So this chapter is going to cover four different parts. Number one is the Gaussian curve. And number two, you have the areas under the normal curve or the Z curve. Next, you have number three, statistical hypothesis testing. And it's also going to cover a few sample problems. So let's begin with the Gaussian curve. So your Gaussian curve is otherwise known as the normal distribution curve, and it has the following properties. First, you have the mean at the center. So let me just pull out my pen here. So you have the mean at the center, you have your mode at the peak, and you have a median that bisects the whole thing. So this would, in a normal distribution, you have a certain level of predictability when it comes to your percentages. When it comes to one standard deviation, 68% of the data should fall between that range. And then you have your two standard deviations, in which case you have 95% of the data falling within that range. And finally, you have your three standard deviations, where 99.7% of all the data in your dataset should fall expectedly within that range. Okay, so next we have the characteristics of our Gaussian curve or the normal distribution curve. So the bell curve should have an equal or at least an approximately equal mean, median, and mode, meaning that the measures of center should approximately be near each other. Now I say approximately because it is very much impossible, or rather improbable, for anyone to consider or for anyone to actually observe the mean, median, and mode to be exactly the same. So at least we can approximate an equal measures of center. And then of course, as with your peak, you should have only one mode since the normal distribution curve or the Gaussian curve only has one peak. You should have a skew of 0 and a kurtosis of 3. So this should be a mesokurtic curve. Now, do take note that some references would note or would reference 0 as the kurtosis. So if you have a negative kurtosis, that would mean that you have a platykurtic curve, and then a leptokurtic curve would be a positively valued kurtosis. In this case, we're going to be using k is equal to 3 as mesokurtic, so anything less than 3 would indicate a platykurtic curve, and anything more than 3 is going to indicate a leptokurtic curve. Okay, so later on we'll talk more about skewness and kurtosis when we're doing statistical hypothesis testing, but do take note that when we meet these observations or when we meet these conditions, that the mean, median, mode should be approximately equal, should be unimodal, should have a skew of 0, therefore it being symmetrical, and a kurtosis equal to 3, then you have your predictable values. Okay, and just to illustrate how observations tend to form the normal distribution curve, we have a sample video from Shutterstock. So in here, you're going to observe the many observations in a pachinko-like setup where the balls are all poured at the center, and eventually they're going to go down and fall within the slots down here. And eventually, as time goes on, they're going to form sort of a normal distribution with with our observation. So do note that this is not a perfect bell-shaped curve, but at least you see you have one peak over here, the center, and you also have a very symmetrical distribution when it comes to your observations. So this is how we approximate our normal distribution, and so we have, or rather, when we have lots of observations and we use a sort of a normalized observation, we can approximate a bell-shaped curve. So now that we know what the bell-shaped curve is, what the normal distribution curve is, in essence, it's a probability distribution curve. It can be otherwise referred to as your Gaussian curve. We can now discuss the areas under the normal curve. Now, as mentioned above, you you have a figure that looks like a bell. Such is the reason why it's also referred to as the bell-shaped curve. And since it is symmetrical, it's divided into two, and its total area is 1. Okay, since we've divided into two, you have zero point 0.5 on the left side and zero point 0.5 on the right side. So that division means that if you add, of course, your zero point 0.5 and zero point 0.5, you get the total area 1.0. Okay. Now, these are the z-scores, which we're going to be using later, or um, the reference of the areas under the normal curve that a certain z-score covers. Now, do take note that there are different iterations of this table. There are z-scores, or there are areas for the left tail, areas for the right tail. This table in particular that we're using is the area from the center going to the z-score. So do take note of that, because sometimes you might use, or in some cases you might use a different z table, and you might have, or you might compute for a different area. Okay, but in essence they are all correlated, so they are just different iterations of the same values. Okay. So next is our formula for z-score. So when we compute for z-score, simply is your data point represented by x minus mu, which represents our mean, all divided by the standard deviation. And just to illustrate this further, let's have a sample problem. Now, in the preliminary examinations for biostatistics, the students scored an average of 67 with a standard deviation of 8.71. So we have to find the probability of a person scoring more than 90. And so we can use our formula for z-score. Now, we've already identified and circled the relevant values here. So you have your mean, you have your data point, and you have your standard deviation. So all we have to do then is to substitute the values for the variables, and we get this formula. And if you input that in your calculator and do make sure that you're following the right order of operations, we get 2.64. And now we can use this z-score to look for the specific area under the bell-shaped curve that we are trying to reference. And by using that area, we can then find out the probability of a person scoring more than 90 in the exam. Okay, so let me show you how to do that. So we have here a copy of the z table I showed you earlier. So your first two digits, your whole number, and your first decimal is going to be referenced from the first column. So you can see 2.6 highlighted in red and 2.6 over here. And then your second decimal is going to be referenced from the first row. So you have 0.01 and we have 0.04 over here. So we're going to use their intersection. We're going to take that 0.4959. Let me just zoom that in. And then we can use that, since again this is a z table that we're using, that references the area from the center to our z-score. Our z-score is over here. Then this whole area is 0.4959, or if we convert that to percentage, that would be 49.59. Now remember that since the curve is symmetrical, we're going to have to add another 0.5, since that would be the area of the other side of the curve. That would give us 0.9959 or 99.59%. Okay. However, let's go back to the sample problem. In the preliminary examinations for biostatistics, the students scored an average of 67 with a standard deviation of 8.721. So, what we're looking for is the probability of a student scoring more than 90. And so far, what we've computed for are the probability of a student scoring less than 90. So 99.59% falls below the score of 90. So what we can do then is, in fact, we're looking for this small portion over here. So what we can do is simply subtract 0.9959 from 1. And finally, we get 0.0041. And of course, that would cover the very, very small portion over here, since it has simply just 0.41% of the students would most likely fall, or would get a score above 90. Next, we have, what if we need to look for areas between both extremes? So what we're looking for here, or this time, is the area between the two extremes, so between the left and the right tail. So let's have another sample problem. Okay, so in the midterm examination of students taking biostatistics, the average score is 72 with a standard deviation of 7.97. So find the probability of the scores ranging from 63 to 87, again using the formula for z-score to determine where exactly in the curve these scores can be located. So let's identify first the given values. Now your mean is 72 and your standard deviation is 7.97 as circled here. Now, the only difference from the first sample problem is that this time we have two data points. You have 63 and 87. And since our formula does not allow for the input of two data points at one time, we're going to have to apply it twice. So you have z, this is your first data point, 63. This is your second data point, 87. And then you simply input minus the mean of 72 divided by 7.97, you get negative 1.13. Now, if the value is a negative, or if our integer is a negative, then that means we're referencing the areas on the left side of our curve. So from the center, going to the left side of the curve. And if the value is a positive, we're referencing areas from the center going to the right side of the curve. Okay, so let's see from our z table earlier. Now I've cut this down so that we have our z values specific for our computed z value. So you have 1.13 and you have 1.88. Okay, let's zoom that in, and you have 0.3708 and 0.4699. Now, since we're looking for the range of, or rather the area of the normal distribution curve from 63 to 87, so you have, example, 63 over here and 87 over here, then all you have to do is look for this area. Then all we need to do is add our values, and we get 0.8407. Okay, so again, convert that to percentage, that would be 84.07%. finally, we have statistical hypothesis testing. So for statistical hypothesis testing, we have three steps. The fourth step being our interpretations or the writing of your interpretations. But let's focus on the three steps first. Number one, we analyze the problem. We establish the facts and determine what you need to work on. So from this sample word problem, determine if there is a significant difference between the exam scores of Group A and Group B from Section 2A. So identifying the relevant information means that we're trying to look at the different groups, whether it be independent or paired, and we're looking for also what we're testing for. In this case, we're testing for difference. So it's as simple as that. All you have to do is identify what you're trying to test for. These are the information that matters because this is going to allow us to help or allow us to select the test that we need to look for or we need to use for this specific data set. Okay. Next, we organize our data. And if it's not already organized, then you would have to tabulate your data for you to be um, for it to be easier to access. Next, we formulate our hypothesis. Now, we have two different kinds of hypothesis. You have your alternative and you have your null. So your alternative hypothesis is a positive hypothesis. So in this case, since we're looking for difference, our alternative hypothesis is that there is a significant difference between the exam scores of Group A and Group B from Section 2A. While your null hypothesis is simply a negation of your alternative hypothesis. So what we're negating is that there is no significant difference between the exam scores of Group A and Group B from Section 2A. So remember that when you formulate your null hypothesis, you don't write a contradicting statement to your alternative hypothesis. Simply, you add words of negation to your alternative hypothesis. In this case, we've added the word no to make it so that we negate all the possibilities except our alternative hypothesis. Okay? And by the way, this is what we refer to as a two-tailed hypothesis. A two-tailed hypothesis would have an area of rejection on both sides of the curve. In this case, you have an area of rejection on your left and an area of rejection to your right. So later on, when we're doing actual statistical hypothesis testing, we're going to be learning more about the areas of rejection. But for now, remember that you have a two-tailed hypothesis and a one-tailed hypothesis. So let me show you what a one-tailed hypothesis looks like. So this is another sample only, but remember, this is not in any way related to the sample problem I showed you earlier. So this is just how a one-tailed hypothesis is formulated. So you have your alternative and your null hypothesis, same as with your two-tailed. Um, However, in your one-tailed hypothesis, you have the assumption that one variable is not only significantly different with the other, but also greater than or less than. Okay. So the difference between two-tailed and one-tailed is that for one-tailed hypotheses, you have an assumption that one variable is greater than or significantly greater than the other. Okay. And the same goes for our null hypothesis. You don't write a contradicting statement. You don't say, in this case, our example is greater than. So you don't say in your null hypothesis that variable x is less than variable y. So because that would be incorrect. And that would not consider our um, equal, or that would not consider the possibility that x and y can be equal. Okay, so again, when you formulate your alternative, your null should be all of the possibilities except for the alternative hypothesis. So in this case, we want our null hypothesis to consider also the possibility that your variable x, is equal to your variable y. So instead of saying less than, we say not greater than variable y, because that would also consider a possibility where variable x is equal to variable y. Okay, so next is when we have a one-tailed hypothesis, that means that we're simply using one tail of the curve as our area of rejection. Again, for our area of rejection, we're going to be discussing this more as we move forward, but let's just know that when you have a one-tailed hypothesis, you only have one area of rejection. Okay? And to determine, or rather an easy way to determine which tail we're going to be using, may it be the right tail or the left tail, is to look at where the mathematical formulation of your alternative hypothesis is pointing at. So in this case, it's pointing to the right, so we use the right tail. So it's as simple as that. Okay? All right. So let's go back to our two-tailed hypothesis. So, just so you know, your two-tailed hypothesis is also referred to as a non-directional hypothesis because there is no direction. So, whether your computed test statistic is negative or positive, you would either get you would get your area of rejection. So, let's say if your area of rejection, or rather your computed test statistic is 2.5 and your critical value is 1.96. Okay, so it doesn't matter if your 2.5, your computed test statistic is positive or negative because you have tails, areas of rejection, on both sides of your bell-shaped curve. Unlike with your one-tailed hypothesis, it matters if your answer is positive or negative, because if it's positive, then this would be to the right. And if it is negative, then it would be to the left. The second to the last step we're going to be discussing is selecting and performing the test. So in this case, you, you would have to select the test that you want to use, either a parametric or a non-parametric test. So that would depend heavily on the data that you are working with. And of course, that would depend also on the distribution of the data, as well as the interactions that you're trying to look for. So for parametric tests, your distribution should be approximately normal. And again, we're going to be talking more about this when we do actual statistical hypothesis testing. But for now, I'd like you to note and remember that some of the tests, or rather a lot of the tests, are robust, or at least they are resistant to violations of normality. So there are ways we can work around the normal distribution, but there are other assumptions that are a lot more strict when it comes to testing parametric. Okay? And for parametric tests, we usually and typically compare means, and then we typically use interval or ratio level data. Now, I use the term typically because there are times when it's important to consider that maybe an ordinal or a nominal data set could be used for a parametric test. Now, that would be a heavy asterisk because it would require some transformations, but it is in fact possible. Okay, in contrast with your non-parametric test, where the distributions may vary. So typically non-parametric tests don't really care about the distribution. So regardless of what kind of distribution you have, you can use non-parametric tests. But this, of course, comes at a cost that non-parametric tests are um, usually considered to be of lower statistical power than your parametric test. So parametric tests, despite being a lot more strict, is still very much preferred. Okay. Your non-parametric test compares ranks, modes, or medians as opposed to your parametric test, which compares means. And the typical data for this non-parametric test are ordinal to interval. Okay. Finally, we have writing your interpretations. So when you write your interpretations, I always like to endorse some creativity and the author's choice, of course. So this is just a basic format that I prepared. So these are the important information that I typically look for in a interpretation for statistical hypothesis testing. So the computed test statistic is a value is then you insert the value given degrees of freedom. Later on, we're going to be talking more about the degrees of freedom. And an alpha set at value of your alpha is typically set at 0.05, corresponding to a critical value of, then you have your critical value over here, which we take from tables of critical value depending on the distribution of your data. Now, since the test statistic is greater than the critical value, then there is a significant difference between group A and group B. And therefore, the null hypothesis is rejected or accepted. So, again, the way you write this is up to you. This would be an author's choice, a writer's choice, and the one who's doing this, the interpretations, should should be the one responsible for writing and including all the information relevant to the interpretation. Okay, so that would be for the discussion. Now, let me just show you a few sample problems. Okay, so now we're not going to be solving the sample problems in this lecture video, but please do comment down below in the video your answers for our sample problems. Now, if you have, I'm going to be reading the comment section. So if you have sample or if you have questions or problems with the computation of your z-score as well as the references for the z-table, then please do comment again down below. Okay, so thank you for listening. Thank you for paying attention to our lesson, and good luck with your studies. Now, here is the references if you're interested in reading more about the topic. Okay, once again, thank you and goodbye.